and kind of think about some of how that's a little bit different in the fact, more precisely, that often we can't use the precise nibbles. But let's get into that. So just to quickly review, for those who are new, and I do see some new names, yesterday we talked a bit about why you want to create an address plan for IPv6, and that basically it allows you to have smaller routing tables, you can implement security policies, you can work on different ways like that. One of the big things we need to think about again in IPv6 address planning is we're not worried about the host portion. In IPv4, that was always a big focus, but in IPv6, generally, most people are not going to have to worry about 18 quintillion hosts, and so we can generally forget about that part and think really strategically about how we want to use the subnet part. Yesterday, I spoke a bit about how you typically have an IPv6 address, which has a prefix and a host. For an individual device, it's going to be a /64 almost all the time, and that allows 64 bits or 4 blocks of hex digits for the device ID and 4 blocks of hex digits or 64 bits for the prefix. Now, we talked about network prefixes and the fact that when you are allocating IP addresses out for a network, you're typically given, in most places, a /48, which will be the first 3 blocks of IPv6 addresses, if we think about it. So the first 3 blocks would be the network address, and then you would have subnets underneath that. So at a very high level, typically your local internet registry or ISP will receive a /32, which they would then break out into /48s, which would be given out to organizations who would then give it out further into individual actual networks that are there, /64s. If we look at a /32, it's typically the first 2 blocks of hex digits, which is again the first 32 bits or the first 8 hex digits, if we want to think of it that way. And then you would have a subnet and the host again. With a 48, we break that down. Now, yesterday we talked a bit about how you might break things down for subnetting on what we call a nibble basis. And a nibble is the individual hexadecimal digit. And so you can see here a /48 lets you use all of these digits, the 15PC in this example. A /52 lets you use 3 of those as a subnet. A /56 lets you use 2, and a /60 lets you use 1. Those are the things. We talked about how these are the common prefixes that we use and the number of subnets that you can get. And these slides are available for you to download, and we'll have them up so you can be able to see that. We talked about a common allocation you might have. If you received a /48 at your core router, you would have that /48 which you'd be able to allocate to your entire internal network. Now, if you have sub-router, network you typically would do, you might allocate a /52 to each of the regional routers, who in turn might allocate that perhaps into, again, routers that are underneath that, or they might allocate it directly out to individual sites, as shown here, where they might do a /64 for each site, and that would be for those individual LANs that are there. We talked also the importance about using a nibble. A nibble is 1 hexadecimal digit. And just for your own sanity, it makes it much, much simpler if you set up your subnet based on the nibble level. So if you use these things like we talked about, where you have a /48, a /52, 56, 60, etc. If you use those, it'll just be a lot easier as far as knowing when a subnet starts, when it ends. It's very easy to increment that and do that kind of thing. You don't have to, as we'll talk a bit about more today. Here's some examples of very simple subnets. In this case, the first of the digits is being incremented in the first of the hex digits, and so you're just going to go with DB8 1234 1000, 2000, 3000. You can do something like that. You could allocate it on the last digit, whatever. Something. Using nibbles again makes it very easy to go and do. The key point is that when we think about subnetting in IPv6, we're really only talking about modifying, for most people, those the four hexadecimal digits that are there. That's 16 bits. That's what we're going to use to make up our subnet. So part of what we talked about yesterday, again, was looking at how do you plan to use those 4 nibbles. How do you, what are you going to go and do? And there is, again, no right answer. This really depends on how you want to set it up and what you're trying to optimize your network for. Are you trying to optimize your network for routing? Are you trying to optimize your network for security policies? You know, what do you want to do? What is most important for you? So when you think about how you're planning out your IP address, your IPv6 address blocks, part of the thinking is to understand what is the highest priority for you. Do you want the smallest, most efficient routing table, or do you want security policies that you can implement on a subnet level? And another practical, as I mentioned there, you know, if you only have 2 locations, then it might be very easy to go and do that. I do need to ask if you could mute, please. There's somebody on here who is not muted. I would like to ask you to please mute. Okay. Okay, thank you very much. So, gave a couple examples yesterday. I just want to quickly review those. One idea was that you could use 1 nibble for the location, 1 for the use type of person. Okay. And another one, then you could have a number of individual networks that you could assign out. A similar take on that would be if you had many different locations, you could use the first 2 nibbles for which kind of location you're at, another one for the use type, and another one for the individual networks. And you know, you can get into all sorts of permutations of this. We talked about the idea of using, you know, 1 nibble for a business unit, 1 for applications, you know, 1 for the region, and 1 for individual sites. And so now you're using all 4 nibbles for a particular purpose. Again, you could, you know, reverse that. Another example would be using applications first. And this is, again, an example where you might want to, you know, your highest priority is that you want to be able to implement security policies or network management policies on an application basis. So, for instance, to prioritize voice or prioritize video or something on that line. So you might want to go and do that. And again, this is the example over here in the slides. So you're focusing on this. Now, we also talked that there's ways of when you go and number those subnets, and you look at that, there's several different ways you can work. You can just start numbering the subnets by incrementing by 1. So you can go and just do 1,000, 2,000, so on and so forth. You can do that. And that may be perfectly fine for what you're doing. It may also not, one of the questions may be, does it provide enough capacity for growth? And this is where you start to get into intricacies with, do you want to make a efficient routing table? Because if you have two networks that are behind the same router, you could conceivably give them a different subnet that would make a smaller routing rule at the top level. So there gets to be some more complexity than we have time to talk about in this brief webinar. But I mentioned this, that you may want to think about, do you just number them? Do you use something like the mechanism described in RFP 3531, which deals with doing what's called sparse allocation as far as jumping around like that? Do you just randomly choose subnet numbers that are in there? It's kind of a question up to you. So again, to calculate the number of required subnets that you want, you need to think about what is the primary factor, what's the primary key you're going to use to assign, to create this address plan. And is it the location, for example? How many locations do you need? Rounding up to the nearest nibble, and then deciding if you're going to continue with those kind of things. We talked again about how many nibbles to use. If you use 1 nibble, you can get 16, 2 nibbles, 256, 3 nibbles. You know, if you're using all 4, you can have a full 65.536. We also mentioned that there are other subnet schemes that are out there. Rather than doing the mechanisms I talked about here, where you're assigning on location, use type, business unit, that type of thing, some places may want to go and use VLAN numbers. They already have them, if they've already set up a mechanism where you can go and do that. Or you might want to mirror the IPv4 networks that are out there. In some cases, you might have point-to-point or inter-router links. And there is a suggestion that for some traffic efficiency, you might use a /127 prefix when you're assigning the actual interfaces and the addresses. But you may want to, though, reserve a /64 for that particular link on the network. Anyway, we can talk about more of this in questions if you'd like to. I want to talk a bit more about subnetting at an ISP or LIR level. Now, just one final note. Again, you can subnet on non-nibble boundaries, meaning that you don't have to just line up exactly with one of those hexadecimal digits. To do that, for instance, you can calculate the number of bits, find the nearest power of 2 greater than or equal to. So if you have 6 locations, 8 is the closest, you need 3 bits. Just the challenge is you need to start thinking about what does it look like as far as the actual subnets and the pieces that are there? How does it wind up being spaced out? Because you are going on different boundaries than you would on on the actual nibble itself. And here it shows using 3 bits for a /51, and so you'd wind up with a range as we show there, some of the examples. But anyway, let's go on and talk a little bit about the ISP level and an LIR level. Now, this is, very typically, it's not much different than what we talked about, but typically the customers of an ISP or an LIR receive a /48. That's what we've talked about in the party yesterday in the beginning parts of these slides. Now, if you think of that, again, it's a prefix followed by a subnet, followed by a host ID. Now, at the ISP level, or the LIR level, you're getting a 32, and so you've got 32 bits that you could use for subnetting. The reality is it's typically going to be, if you're passing out /48 to your customers, then you're going to have, again, another 16 bits of subnetting that you can focus on. And so again, you can focus on there, and so it's really, on a certain level, not that much different than what we just talked about with the /48. The difference is it's with the 3rd block of hexadecimal digits rather than the 4th block. So it's on that, in that 3rd block that in my example is 1, 2, 3, 4. And so you look at that and you say, well, how many subnets do I want to allocate? If I have a /32, if I want to allocate to somebody a /36, then that will give them 4,000 /48 subnets. Or that customer could then further subnet that into 16 /40s or 256 /44s. If I want to give my customer a /40, okay, which would be using the first 2 nibbles that are part of that 3rd block. If I give them the first 2 nibbles, they can then have 256 /48 subnets in their environment. Or they could subnet it further themselves and do 16 /44s. And you could see on from there, if I gave them /44, then they could have 16 /48s that they could go and do. So it's really a question you have to ask is, for this given customer, how many /48s do I want to give them? And if the answer is just 1, if they're just a large enterprise or an enterprise that they can do everything they need to do within 1 /48, which, to be honest, is going to be a lot of your customers, probably most of them, then you just give them 1 /48 out of your allocation. Boom, you're done. If they need, several different /48s for a very large network, then if you want to, you could go on the nibble boundary and you could go and give them, a /44 and use that last nibble as the increment for the subnet. So you just, change it by 1 or whatever you want to do in there. That's the part that you can go and do there. So if you use nibbles, again, it's very simple. It's very easy. And the nibble, again, is a hexadecimal digit there. Now, you can start to get into subnetting this down at a bit level. So again, if we think about that 3rd block of hex digits, each one of those digits actually represents 4 individual bits. So, and you've got, and I've shown here what 1, 2, 3, 4 would actually be, but you've got this idea that each of those hex digits is actually 1 individual bit. So now from a routing level, if you want to start assigning subnets, you can work on the on any number of bits. You know, we use /32, we use /48, /44, /40. You know, we use these as just convenience, but we can use any value we want. So to look at this, I find personally that it's just helpful to think about how many subnets do I want, and that tells me how many bits I'm going to use. So if you look at that first chart on the slide, it tells me the number of bits and the number of subnets I can get. So if I want to use 10 subnets, I would need to use 4 bits. If I want to have, 200 subnets, I need to use 8 bits. If I want to use 100 subnets, I need to use 7 bits. Now that's how many bits you need to use in order to get that many subnets. Now, for the purpose of subnet creation, it may be more helpful if you kind of turn it around and think of it in this reverse order, because that's the way that you're going to be seeing this. Now I do see. I should say I see a hand up from Ola Abacha, who I think is also sending us video. If there's a question, please do feel free to. Ola, do you have a question? Okay, you have raised your hand, and if you do that, we do notice that, and we can ask. We can do that. Okay, you've pulled your hand back down. All right. To everyone else who's listening, if you do have a question, we will have a time for Q&A later in here, but you're welcome to as well raise your hand as we go through this. So just to kind of look at this, if you use a certain number of bits, you'll have a certain number of subnets, and you can use a prefix. So if you look at this little chart I've given you here, this little cheat sheet, it shows you that if you look at the far right side of that, and you back up a bit, you want to have 2 subnets. If you look at that middle row, the number of subnets there, you want to have 2 subnets, and so that means you're going to use 1 bit, and so you'll assign out a /47. If you want to break it up into 4 subnets, you would give out a /46. You start calculating it this way. Now, as a note in that bullet below there, you start to look at if you subnet on a /44, you'd have 16 subnets, so you could use that entire last digit, the last number, as far as your increments. So you could give somebody 1231, or 1230, 1231, 1232, 1233, 1234, etc. All of those would be 120, 120, 121, 122, 123, 124, etc. You'd be going on that nibble that's in there, a third nibble for a /44. Okay, so the question that you get into, I'm sorry, no, I was correct here on the last nibble. That's cool. Confused there for a moment. If you get into assigning individual ones, you start to move the boundary. So for instance, on this slide here, I show you what it would look like if you did a /47. You would have 2 subnets, and the subnets you would allocate out to those networks would be, as I show there at the bullet item, 2001 DB81230 /47, which would be the address range between 1230 and 1237, and then you would have 2001 DB81238 /47, which would be the range from all that 1238 up to 123F. For 4 subnets, you would then, again, you're going from 0 to 3, 4 to 7, 8 to D, C to F in terms of the last digit there, the last nibble. So it gets more complicated, which isn't to say you can't do it, but just is more that you have to be thinking about when you go through this. And that's really the basics of how you can get to working with that. Now, one last note before I wrap this section up and turn it over to Hisham to talk about technology transition. Many ISPs can just request a 32, and that's what you'll get. So think of it again, it's the first 2 blocks of IPv6 addresses, of hex digits. You can request a larger space. Hisham was talking earlier yesterday a bit about what the AFRINIC will allow. And the question really is, how many /32s do you want to have? So if we look at this, again, if you want to request more than a single /32, if you look at this chart, again, now you're doing the number of bits in that first or in the second block of hex digits. And so you have those sections there, and you need to think about, if you use X number of bits, how many subnets will you have, and what will you do? So if you look at this chart I have right here, and go from the right side, if you want 2 subnets, or if you want 2 /32s, you would need to go and request a /31. If you want 4, you would need to request a /30. If you want 8 /32s, you would request a /29, and so on. The pattern goes on like this that you can go and do. So that's all I'm really going to talk about right here. What I want to talk about, oh, interesting. There was another chart that was supposed to be in there. Okay, it's all right. What I want to just wrap up to say, or what I want to finish with this to say, is that, you know, talk to Hisham and the folks at AFRINIC. Their staff there can help you if you want to figure out what higher amount of IPv6 address blocks you need. Think again that typically a customer is going to receive a /48. That's what they're going to allocate out in the ways that we talked about earlier. And they may want, you know, if you're fine with the /32 that you may be typically given, that can work fine. If you want more address space, you need to think about it in a bit form, and how much do you want to request? What are you looking to do? So let me close and just, again, mention some of the recommendations that we have in general, which is to ensure that the prefixes fall in nibble boundaries. That will work best for you, even if you're requesting additional space from AFRINIC or another RIR. It will be just easier for you in the calculations and the planning of what you're doing and how the individual subnets work. You also can plan a hierarchical scheme for the aggregation enforcement policy. Think about how you want to structure it. If you're going to, do you want to structure it on location? Do you want to structure it on application or end user? Allocate /64 prefixes for all the end subnets. And think about scalability. Think about what would happen if you grow more in this. Will your scheme work when you go and do it? Similarly, think about what would happen if you decide to change ISPs. How well would your plan renumber? How would it work in there? What would it do? And again, always document your planning very thoroughly in the way that you can. So I'll just finish up with some resources. Again, the folks at AFRINIC who are sponsoring this webinar have a series of resources, a whole series at this URL that I put here, learn.afrinic.net. These resources there. One of these and slides we used in the slides yesterday are part of the foundation class. Excellent resources for you to take a look at and see, and good information around this. The folks at SurfNet worked with the RIPE NCC, the European Regional Internet Registry, and have put together a good document called Preparing an IPv6 Address Plan. And also at our organization, the Internet Society Deploy 360 program, we have a series of documents up, and later today we've just actually published a new resource around IPv6 address planning, and that will be up on the site in about an hour or so. So with that, I will turn it over to, I will say thank you very much, and turn it over to Sean to talk about IPv6 transition technology.
And I'd like to voice again what Dan was mentioning at the end, that AFRINIC's hostmasters are more than happy and more than capable to work with you on your address plan. What we described here is how, or Dan actually described yesterday and today, was how to do subnetting and how to do your address planning. However, if you feel that you're not that confident yet in putting together your exact figures, feel free to contact AFRINIC's hostmasters. They will walk you through the math, they will walk you through your exact case, and they are more than happy to do this with you on a case-to-case basis. We have allocated, like Dan mentioned, space bigger than a /32. We've allocated all the way up to a /20. Yeah, there are cases of that, and we're more than happy to work with you to find exactly how much space you need for your organization. Moving along. This part of the webinar will be discussing the different transition mechanisms that are out there. And the first question that comes to mind is, why do we actually need transition mechanisms? Why do we need an IPv6 transition mechanism? And to answer that question, we need to take a step back for a second here and discuss coexistence. What does coexistence mean? You may have heard Kevin yesterday talk about the RIRs, or the regional internet registries, which, as you can see from the map here, serve different communities and economies and regions. So you have AFRINIC that serves the African region. You have AFRINIC, which serves the Asia-Pacific region, the one in gold on your right. You see ARIN that serves the North American region, LACNIC, Latin America and Caribbean, and the IPv6 for Europe, Middle East, and Russia. So each one of these RIRs manages the internet number resources pool, whether it's IPv4 or IPv6 autonomous system numbers for that particular region. And LIRs, ISPs, and M sites can only request from that RIR, from that region. You cannot, from Africa, for example, you cannot request space from another RIR. So, and also this was touched on yesterday by Dan, is the IANA function. Think of IANA as the main pool, the main reservoir that has all the unallocated internet number resources, be it IPv4, IPv6, or autonomous system numbers. Gives huge blocks of the space to the 5 RIRs. So if we're talking IPv4, we're talking about /8. If you're talking IPv6, each RIR, as was mentioned yesterday, has received a /12. And these RIRs start giving them out afterwards to the LIRs, the ISPs, and the M sites in the region based on the policies that were developed per region. So what happened was on February 3rd, 2011, the IANA ran out of IPv4 addresses. They exhausted the main reservoir. That pool had no more /8s out to give to any of the RIRs if they requested. Based on a global policy that was put in place, but what happened was, like I said, there were no more /8s to give out to the RIRs. So each RIR had some space left, and it was distributing it to its region based on the policies that it had there. As you can see so far, 2 of those RIRs, 2 of those 5 RIRs have hit their final /8. So the Asia-Pacific region in April 2011 and RIPE-NCC in September 2012, they both reached their final /8, which automatically means a new policy kicks into place where users, ISPs, new members, or even old members cannot request a lot of IPv4 space. They can only request a certain amount of space, and after that, they're asked to go to IPv6. So in these 2 economies, in these 2 regions, a lot of people now are moving to IPv6 simply because they cannot get more IPv4 from their RIRs. So when we usually represent the internet, we usually draw a cloud. However, we all run networks. We all know that internet isn't just this big cloud. It's actually, there is no one big internet. The internet is a bunch of different networks that interconnect together. These networks communicate together if we're talking IP, so it's either IPv4 or IPv6. Each network has an ASN number, and that's how packets get pushed back and forth all over the internet. So the case that we have now is we have networks, the majority of the networks have IPv4 space that we use to communicate since the beginning of the internet up till now. Some of them have now both IPv4 and IPv6 on their networks. You can see some of the clouds that have both of them. And some of them are on IPv6 only now because of the fact that they cannot get more IPv4 resources for their needs. Well, their network is growing to an extent that IPv4 cannot serve anymore. So as you can see, it's clear that IPv4 and IPv6 will coexist for a long time on the internet. It's not like IPv4 is going away anytime soon. IPv4 will be there and IPv6 will be there. So to answer the question that I proposed a couple of slides ago, why do we need IPv6 transition mechanisms? The answer is because IPv4 and IPv6 are not backward compatible, which actually means the IPv6 only network that you see on the top there cannot talk to one of the IPv4 only ASN's networks. They cannot communicate directly to them. It can communicate with the IPv4, IPv6 ASN. The IPv4 can communicate with either IPv4 or the IPv4 and v6 networks. But the v6 only and the v4 only cannot communicate together with each other. And that is why the need for transition mechanisms to address that coexistence period that we are actually living in now emerged. So an example I usually give while I'm teaching these slides during trainings, I don't speak French, which is one of the two major languages spoken in Africa. It's either English or French. These are two dominant languages. There are a bunch of other languages, but French and English are the most dominant. I don't speak French. So if I have a person that only speaks French in my class, we cannot directly communicate together. It does not work. Think of it as IPv4 and IPv6 not being able to communicate together and not compatible together. However, my colleague Bryce, that did the French trainings webinar, speaks both English and both French. So he's bilingual. So if somebody comes up to him and speaks to him in English, he can reply back in English. If somebody comes up to him and speaks in French, he can reply back in French. If somebody knows both French and English, they can choose whichever language they're comfortable communicating with, and they use that to communicate. And that concept of being bilingual in the network world is called dual stacking. And we're going to look at this from a technical perspective. This is just to go through, common sense of how two devices or two people can actually communicate together. So dual stacking means having the ability of speaking both IPv4 and IPv6 at the same time. Another proposed technique was doing translation. So because I don't speak French, if somebody that speaks French needed to speak to me, we needed to have a translator in the middle. We needed to have something or someone that's in the middle that listens to what I have to say, converts it into, or translate that into what the other side would understand, and do the same on the way back, vice versa. So in IPv4 and IPv6, you'd have a translator that translates back and forth. This is some of the ways that people started thinking, and we're going to examine this from a technical perspective now. So for the IPv6 transition mechanisms, you have, for the migration to IPv6, moving to IPv6, you have dual stacking, which we discussed, which basically means hosts call IPv4 and IPv6 independently to whom they are talking to. So they can speak both IPv4 and IPv6 fluently, and they have no problems with that. The second kind would be tunneling. Tunneling is basically, think of it as having a pipe between two networks. So let's say both of them speak IPv6, and the networks between them don't. They speak IPv4. It's like putting up a pipe between both v6 networks. That v6 traffic can go through that pipe, regardless to what the networks in between support or do not support, so that they can communicate on both sides of the pipe over IPv6. That's basically what tunneling is. Or you can access IPv4 content over IPv6 terminal and vice versa using translation. So dual stacking, first kind. Dual stacking is the most straightforward option that you have. It's basically doing everything that you're doing on IPv4 and taking it and doing it on IPv6. So if you look at your network, for example, you would find your hosts, your terminals that understand IPv6, your switches understand IPv4 and IPv6, your routers, border routers, firewalls, all your different elements on your network understand both IPv4 and IPv6 and can deal with an IPv4 packet and an IPv6 packet in the same manner. So that means if you're doing configuration, you're configuring, if you're doing, let's say, for example, BGP, you're doing BGP for your IPv4 families and you're doing it for your IPv6 ones. If you're doing firewalling, access lists, if you're doing everything you do for IPv4, everything you use, all the different tools and all the different appliances and all the different protocols that you have implemented on your network for IPv4, you do the same for IPv6. This is sometimes easier said than done for some vendor reasons. Some of the vendors aren't as mature with their IPv6 protocols as they are with their IPv4. However, this is the ultimate end goal. This is what you should strive to do, that you can actually have your appliances, your equipment that understand both IPv4 and IPv6 now. One thing that I'd like to mention on this slide is, out of experience, out of best common practices that I've seen people do, is I actually think it's best if you're going to do something like this, that you start from your border router and you work your way in, not the other way around, not start from in working your way out. The reason behind that is because I've seen this a bunch of times where people would turn on IPv6 at their, I don't know, somewhere in the middle of the network, or they turn it on their hosts and desktops and stuff like that. And then they come back and complain about performance. And the reason behind that isn't necessarily tied back to using IPv6 specifically. It's because you're telling them that there's IPv6, so they go and they test it and they time out once and twice and three times, and then they go for IPv4. And that caused something that the technical community was talking about for a while, which was a term called brokenness, which was addressed through a bunch of different things. ISOC, for example, held two events, one in 2011 called World IPv6 Day, and in 2012, World IPv6 Launch, where they had all the content providers turn on IPv6. For the first one was for only 24 hours, and the second one was turn it on and leave it on, to test that brokenness, to see if things would break or not. Things went fine and they did not break. And there's a lot of, I think the statistics are still there. They're taking live statistics, and probably somebody from ISO can share the link to World IPv6 Launch website if anybody's interested to look at the measurements. But anyways, the point I'm trying to make is that if you do it from your border router in, it makes it easier for you to actually do this than doing it from the other way around, so that your appliances do not get confused. Yeah, thank you, Dan. The URL is on the chat. Yeah, so this is selection stack on the dual stack router. So basically, again, like I said, whatever you can do on IPv4, you should be able to do on IPv6. So let's say if you're typing in a URL, and we saw an example of this yesterday, you can use it with the IP address. You type HTTP, you put the IPv6 address between brackets, and so on and so forth. Because the reason why we have this brackets is because with IPv6 you use colons. And so not to confuse it with the port number, I think that was touched on yesterday. Versus, of course, what you do with IPv4, which is HTTP 192.0.2.1. Same thing with ping, same thing with your basic functionalities. What you can do with IPv6 IPv4, you should be able to do with IPv6. When it comes to DNS, so with an IPv4, when a query, you get an A entry, you get an A response. However, if you're using IPv6 queries, you get a quad A response. Okay, the reason why they call it quad A is because IPv6 is 4 times as big, so they call it a quad A record. If you're using dual stacking, so you can either get both an A or a quad A. What used to happen, and this ties back to, again, the brokenness that I was talking about earlier, it was IPv6 was always preferred. So if there was an indication that there was an IPv6 connection, your appliance, your equipment will try it once and time out and try it again and time out and keep on trying it a couple of times so it times out and then uses the IPv4 because it would prefer the IPv6 connection. However, to address that, there's an RFC called RFC 6555, which is Happy Eyeballs, that actually looked into that and said, okay, so what will happen is they will request both A and quad A records, and the one that replies back the fastest is the one that they're going to be using. And that kind of solved that issue there. And you find Happy Eyeballs implemented on different platforms. I think Max Lion has it. I think the new Firefox has it. You find a bunch of different tools and appliances that actually have Happy Eyeballs already implemented to actually address that brokenness issue. And yeah, and DNS responds independent to layer 3. So you get if you query over v4 and you get a quad A, there's nothing with that. So that's basically dual stacking. And like I said, that's the easiest way to go, provided that you have equipment that can actually deliver on both. There's no parity between the features between IPv4 and IPv6. If you have that on your equipment, then you're good to go. Tunneling. Tunneling is, like we said, if you have two hosts that two networks that speak IPv6. However, the networks between them don't necessarily speak IPv6; they speak IPv4. So what happens in tunneling is basically what you need to do with an IPv6. As you can see, this is the IPv6 datagram. The IPv4 header protocol is set to 41. That way, you can add an IPv4 header in front of your IPv6 datagram, and it looks like an IPv4 packet, and it gets routed around like an IPv4 packet. So tunneling, here you can see again, if you have either a dual stack or a native IPv6 network, you can see them on both sides, but the connection between them is an IPv4 only network. So what happens is the IPv6 packets get encapsulated inside the IPv4 packets using the protocol number 41 that we've just mentioned now. The tunnel originates and terminates at an IPv4 address. So to create a tunnel, you need IPv4 addresses at both sides and IPv6 addresses to have that tunnel up there. Tunnel endpoints manually configured for manual tunnel or automatically for tunnels like 6RD or 64. We're going to discuss this in a second. There are different kinds of tunnels. They could actually be either manual or automatic. And something I probably should have mentioned when I first talked about the transition mechanisms is there is no one right way. There is no, this is the best way to do this. You need to examine what you have on your network and see that there's no one size fits all. You can actually take a bunch of different these transition mechanisms and apply different transition mechanisms in different parts of your network. You can deploy, if you can do, for example, IPv6 dual stack throughout your network, that is great. You probably will not be able to do that right away, so you may have to do some tunneling. You need to tunnel through IPv4 only infrastructure that you have to be able to reach that IPv6 connectivity that you're wanting. For example, if your upstream provider does not provide you with IPv6 connection, so if you are one of the oranges in Africa, for example, one of the France Telecom affiliates in Africa, so your upstream provider, France Telecom, provides you with IPv6, so you can have a dual stack connection with them. However, let's say you are with an your upstream provider does not provide you with an IPv6 connection. What you can do is you can tunnel through his IPv4 connection using IPv6. Yeah, again, tunneling, what happens is, so you see your IPv6 datagram up there with your IPv6 headers, with the data information, with the transport header, and what happens is the packet originates from the V6 network, goes to the dual stack router. The dual stack router then forwards it and directs it to the tunnel interface because it's IPv6 going to an IPv4 network. So it gets encapsulated in an IPv4 packet with an IPv4 header, and it gets forwarded to the IPv4 network until it reaches the other dual stack router that actually unencapsulates it again, and it's moved back as an IPv6 packet once again. Types of tunneling. There are different types of tunneling that, as I mentioned, would be different on the services that you offer, the kind of customers that you have, what kind of business are you doing. So, for example, there's manual configuration, and each one has their different benefits. So there's manual configuration, where you go and you configure each tunnel manually. So you go, you put the source and destination tunnel IP addresses on both sides. You configure them for both sides, and you do this one by one, which actually has benefits that, for example, well, first of all, they have to be pre-agreed from both sides for you to actually configure them. And it helps that you actually can determine at any given time where these packets are going, because they're only going through the funnels that you have actually configured. However, the problem with that is scalability. So let's say you are an ISP that only serves a couple of enterprise networks. You can do that with them because they have the big shiny boxes. You can do that connection with them. It's not that many customers, and manual tunneling would be easier for you. If you're like Kevin was mentioning yesterday, our friend Machuki in Kenya has a similar connection with one of the ISPs because he was trying it out with them because he's just one person. However, if we're talking about a DSL provider that's looking into doing this to all its DSL customers, manual tunneling will not be the best way to go because he'll go crazy building all these tunnels all the time. There's semi-automatic tunnels where you go to a tunnel broker, RFC 3053, where you go to somebody like American Electric, for example, that will configure that tunnel for you, or AFRINIC runs a tunnel broker service in some parts of Africa. So we have a node in South Africa serving Southern Africa, and then one in Kenya serving East Africa. The reason why we did so in Africa, even though there are more tunnel brokers out there, is again it all ties back to the user experience. A lot of people, when they turn on IPv6 and they find that delay occurs, they tie that back to IPv6. They don't tie that back to how packets are actually routed, which is the actual reason why. So with all these tunnel brokers being hosted off continents, your IPv6 packets that go through a tunnel broker leave the continent, go all the way up to Europe or the US or wherever they're hosted and come back. That tromboning effect there is what actually gives you that latency, that delay. It has nothing to do with IPv6. It has nothing to do with the technology itself. It just has to do with your packets are being tromboned off continent and back. I give them the example of Machuki again. that when that actually happened, because the ISP that he was testing with at the time wasn't peering over IPv6. So he would find, even though at the exchange point, so he would find if he wanted to talk to somebody in the next street over IPv6, his packets would still go all the way up to Europe and back because of that. And they actually fixed that by doing peering at the exchange over IPv6. So now he doesn't have to leave Kenya at all. All his IPv6 traffic is there within Kenya. Last kind of tunneling is automatic tunneling. There's a bunch of different kinds. There's 6RD, 64, and these tunnels are created on demand. So let's say you're running a DSL network and you want to have, and I think there's a slide on 6RD now, and you want your customers to actually have IPv6 connections without configuring manual tunnels. 6RD would actually do that for you. They will configure automatic tunnels as long as it needs it, and then bring them down when it doesn't. Yeah, 6RD. So the example I was just discussing of 6RD tunneling is exactly that. So what happens is, if you have a 6RD network, you have your IPv4 and IPv6 capable devices on that. If it wants to talk to the IPv4 network, it uses the IPv4 backbone as we normally use it now. However, if you want to talk to an IPv6 only network, there's a tunnel service over there that tunnels your traffic, your IPv4 traffic. It tunnels it all the way to the tunnel server, and then it's communicates to IPv6. The benefit of using 6RD is all the tunnel traffic stays within your ISP, stays within your network, and you communicate afterwards through your border routers. You communicate using IPv4 and IPv6. That's one way of going if you have large number of, let's say, DSL customers. Translation. In translation, IPv4 formatted information is converted to IPv6 and vice versa. So, for example, so IPv6 translation technologies are different from tunneling because it allows IPv4 only devices to talk to IPv6 only devices. This is something that tunneling cannot do. Tunneling allows v6 only to talk to v6 only, even if the connection between them is IPv4 only. However, in translation, IPv4 only can talk to IPv6 only devices. There are a couple of different ways to do translation. There's NAT that we're going to discuss now, NAT 6.4. There's also application layer gateways that, from the name, actually does this on an application level. So it inspects the packets and looks at the IPs and the ports and actually converts them back and forth based on that. However, not everything was built to support application layer gateways. Does it always work? And there's the delay time. Think of it even as a human being. If I'm speaking and then somebody's translating what I'm saying and then getting the response and translating it back, that's at least twice as much of time. If you're talking about millions, thousands and millions of sessions there, that you will end up with a huge delay on your network, a whole overhead on the devices that actually do so. So yeah, that is why translation, let's say you only use translation only when you really have to. So examples of DNS 6.4 and NAT 6.4. So let's say you have an IPv6 only network. If you're talking to the internet, if you're going to an IPv6 internet network that supports IPv6, then yeah, your packets go out, there's no problem with that. However, if you're talking to the IPv4 internet, then you'll probably need stuff like DNS 6.4 that actually takes the queries back and forth from IPv4 and IPv6. We have a slide about that coming up now. This is just a simplified slide. and you probably will need a NAT translator that does NAT 6 support that translates back your IPv6 addresses to IPv4 and back and forth, so you can communicate with the IPv4 internet. And yeah, this is how it looks. Again, I say it's a big complex. There's a lot going on, and you can actually see with all the different steps that you will end up with more delay than you actually get with straightforward IPv4 creating an IPv4 DNS or IPv6 creating an IPv6 DNS. So what happens is if you follow the numbers, so number one, your host is asking for the quad A record for example.com. So what it does is it goes to the DNS64 server, and the DNS64 server actually goes and asks the regular DNS for the A record for example.com. So the regular DNS replies back with the IP address, which is in this case 192.0.2.6. And what the DNS64 does is it synthesizes a quad A address using a well-known prefix, which you can see here is 64:FF9B:/96. The reason why it's a /96 is because IPv6 is 128 bits. When it synthesizes the address, what it does is you have the prefix and then you have the IPv4 address after that. So the IPv4 address is 32 bits, so 128 minus 32 is 96, and that's why you have a /96 there. So they synthesize the new quad A record here in this example would be 64:FF9B:/, then the IPv4 address, which would be, so the 192 turns into C0 in hexa. The 0 after that turns into 00 in hexa as well. The 2 is 02, or you can just put 2 over there because the 0 right after the column. And 6 is 06 in hexa. So that's how you end up with that quad A record, the prefix and the IPv4 address converted into hexa. You don't have to use the well-known prefix. You can use your globally unique addresses. And if you're using the well-known prefix, please do not advertise that to the internet because it's not globally unique. So this is something that you also need to take into consideration. Do not advertise the 64:FF9B prefixes outside your network. Anyways, going back, so now your host has a quad A record of the website that it wanted to visit, example.com. So what it does is, so step 6 is the source with its IP address, you see, 2001:DB8::2. That's the source. And the destination would be 64:FF9B::, the IPv4 address. It goes to your NAT64 router or device that does your NATing. So the insides of this box is on IPv6, of course, 2001:DB8::1, and the outside is the IPv4 address, 192.0.2.1. So as we all know how NAT works, it moves it remembers the address that came from within the network and sends it out with one of the IPs that it has. In this case, the source now has become 192.0.2.1, and the destination is the IPv4 DNS record that you got, which is 192.0.2.6. So it goes to the website, it queries the information, the website replies back with the web page, and it goes to the NAT box, which then again takes out the IPv4 NATed address, puts the IPv6 addresses, and pushes it within the network back to the host so that it can actually see this. So as you can see, this is like a 10-step process, which takes much more time than you just querying your quad A over IPv6 or your A records over IPv4. So yeah, this slide shows the different categories again. Dual stacking. As you can see, everything is done over both IPv4 and IPv6 to communicate with the IPv4 world or IPv6 world. Tunneling, you can see the pipe down there that connects the servers that are on IPv6 to the IPv6 world, bypassing the IPv4 only network. Translation, everything is over IPv4, but that box translates back and forth from IPv4 to IPv6. And you get to choose what is more suitable for your network, and it doesn't necessarily have to be your entire network. You can have bits of it dual stacked, bits of it tunneling, bits of it using translation. You can combine these together. There's stuff out there like DS Lite, for example, dual stack Lite, that combines both dual stacking and NATs. You can mix and match just based on your needs, your customers, your services that you're doing. If you have, for example, if you're mobile, if you're doing LTE, for example, and you don't want to use it over NATs, and LTE is a very IP-hungry technology. So if you don't want to use NAT because NAT gets too complicated over LTE, and you want to do this over IPv6, and you're probably looking into actually doing tunneling and giving your, provided that the phones, the end devices support IPv6, you can actually tunnel the services back. It all comes down to what service you're actually providing to your customers. Best common practices with this is to dual stack where you can. If you can dual stack, if your upstream provider gives you IPv6, then get an dual stack with them. Do dual stack where you can if your network supports this and if the surrounding elements support dual stack. And tunnel where you must. If your upstream provider does not give you IPv6, if you have appliances in the middle, legacy devices that you cannot replace or do not have the budget to replace yet, you can tunnel through them and translate only where you have to. These are best common practices. My final slide, and then I'm going to go to Q&A, is basically at the end to summarize what we've been discussing for the past 2 days is, so what do you do now? You've been listening to these webinars for the past 2 days. You've heard the perfect presentations that were given by Kevin and Dan. How can you go about doing them now? Well, first step is awareness. And I'm pretty sure all of you were aware coming into the webinars, registering for them, taking the time, that there was an issue. And I hope that through the different presentations that you're more aware of that issue now and why there is need for IPv6 and how you can actually get that on your network. And please take that information and share it with your friends. The webinar that you attended here will be recorded and put online. There's other webinars that have been previously done that are online as well. There's material that Dan has shared. If you can share that internally with your coworkers, with your bosses, with your subordinates, and actually have them becoming more aware of why you need IPv6 and why you should get it on your network, that's step one. That awareness is definitely step one. Step two would be to survey your network. This is something that I always tell people whenever they come to me and say, what can we do with IPv6? You need to look at your network. You need to do inventory and see what do you have that supports IPv6 and what do you have that doesn't. Whether it's terminals, whether it's switches, whether it's routers, whether it's servers, whether it's operating systems, whether it's software, whether it's management tools, whether it's security appliances, firewalls, or intrusion protection devices. You need to do a proper survey to see what supports IPv6, what doesn't support IPv6, and when you see something that supports IPv6, does it support the features that you want, the stuff that you have implemented on IPv4, and you do that on IPv6 or not? That is the most important step that you can actually do. Even if you're not ready for IPv6 today, by doing this, you're doing half of the work. The rest of the steps are very easy. But the biggest part, and that the part that nobody can do other than you on your network, is to actually do that. Survey your network, know what parts can do IPv6, what parts cannot. The parts that cannot, can you, for people that always mention IPv6 being expensive, can you get rid of those through your natural purchasing cycles? Can you, for example, the CPEs for DSL users, can you purchase equipment that's CPEs that support IPv6, and there's a couple of them out now that we can discuss during Q&A, that support that, instead of the ones that do not. If you have, I don't know, VSLAMs that do not support IPv6, can you actually look into getting stuff that can actually do IPv6? All that stuff, you need to properly understand what you have on your network. And like I said, you're in the best position to do that. Nobody can do that for you. And it differs from one network to another, it differs from one place to another. Step 3 would to be build your address plan. You heard the brilliant presentation from Dan on actually how to do your subnet, how to calculate how much space you need. Again, I say our host masters are more than happy to do the math with you to tell you how much space you actually need from AFRINIC, your RIR, or if you need to get it from your ISP. If you're an AFRINIC member, like I mentioned yesterday, the space that you get without any additional costs for your IPv6 users. And yeah, start building your address plan. Start seeing if something needs to be renumbered, if something needs to be done again. If you want to get rid of NAT and take advantage of the fact that AFRINIC still has some IPv4 space left, and build your network properly without NAT and do it over IPv4 and build IPv6 on top of that, like a bunch of different networks did in Africa. What comes to mind is a university in South Africa, Free State University, that actually did that. It had like one flat NATed IPv4 network, and they took that and they redesigned the entire network with VLANs, with subnets, and instead of having a flat network, they built a proper architecture, and they got the IPv4 space that they needed from AFRINIC. They had the university discount that I mentioned yesterday, 50% discount, and they got the IPv6 space that they needed, and they very easily, after they did the IPv4 redesign, they very easily just put IPv6 on top of that, and now they have a fully dual stack network in that university in South Africa. Step 4, yeah, okay, so I kind of said step 3 and step 4 together. So once you do your plan, you need to get your resources from either AFRINIC, or if you're dialing in from other continent, from whichever area you belong to, or your ISP. If you do not qualify to get space directly from AFRINIC because your organization size is too small as an end site, or your service provider doesn't have, cannot qualify in one of the different membership categories, then you need to get it from your ISP, and your ISP gets it from AFRINIC. Enable IPv6 and start testing. Once you get your space, easiest thing to do, it's like a 2-comment thing on your whichever box you're using. You can get IPv6 enabled. You can start advertising it. People can actually start seeing your network. And if you remember the graph that I had yesterday with the ASNs that support IPv6, you become a dot on that. People actually start seeing I can reach that network over IPv6. Step 6 is implement the transition mechanism that best suits your network. Like I said, there's no one-size-fits-all scenario, and based on your needs, your customer needs, your network, your topology, you should choose what is best for you and go with that. So on that note, thank you very much for listening, and Kevin, I'll leave it back to you to take Q&A.
Thanks very much, Hisham and Dan, for those very, very good presentations. Those are excellent. So I have a couple of questions, but before I ask them, I'd like to invite questions from the floor. So if you have a question, you can raise your hand or you can post a question on the chat. Okay, I don't see any hands. Maybe as we think of the questions, let me ask. Let me start with you, Hisham. So for maybe someone who's listening and works for a company and they want to get their own IPv6 address block from AFRINIC, what are the? How long does it take? What are the costs involved? And what's the procedure?
How much time it takes? I think that we are striving. I'm not sure of the number that I'm just going to say, but I think we have a maximum 48-hour reply policy. I'm not pretty sure of that number exactly, but I'm pretty sure you get a reply within a day, maximum 2. So if you mail hostmaster@afrinic.net, you will get a reply from our hostmasters. If you want to become a new member, there's a mail for new members. I'm going to get all that information put on the chat now. There's a mail that you can mail, a mail address that you can mail to our member services liaison that actually walks you through the process if you are a new member. If you are an existing member, then you mail the hostmaster. You get assigned a NIC handle, and you get assigned that you can actually communicate with them saying, this is my NIC handle, and they can pull up all your information that we have there. And you can say, okay, I'm expanding my network. I want to get rid of NAT, so I want to do IPv4, or I need IPv6 space. And they will be very familiar with your case. You'll find people that actually have dealt with your organization and remember it quite very well. There's an FAQ on how to become a member and benefits of becoming a member and what you can actually do and the different fee structure, because it depends now. The way that the fee structure at AFRINIC works is based on how much IPv4 space that you have. You get put into different categories, and based on that category you are built. It has nothing to do with your IPv6 space. So if you are a member, you get your IPv6 for now for free. That may change afterwards with the different business models, but for the time being, you get IPv6 free of charge. What else can I say about that? As a member, you have access to My AFRINIC, which is a portal that you get to actually manage your space. If you want to register how you're using that space, which is always a good thing, and I can explain why if anybody has a question on that. You can actually do that by yourself. You can actually have, there's I think a button that you can, if you have your NIC handle and you access My AFRINIC, there's a click here to get your IPv6 resources button without even having to go through the emails and stuff. And it generates that email for you and sends it to the hostmasters. So yeah, there's a bunch of different benefits of doing so. You get the trainings. We do the free trainings in, like I mentioned yesterday, at least 10 to 13 countries per year. So, and our members have priority to attend these trainings. So there's a bunch of different benefits there. I'll put the URLs and the emails in the chat now, but yeah, I hope I answered your question.
Thanks, Hisham. Any question? You can also unmute your mic and ask a question. Okay, I don't see any hands, so I'll ask my second question. My second question is to Dan. That was a great presentation describing the different options available for subnetting. What advice you would give someone just starting out with IPv6? Is it better to there are a lot of free web-based subnet calculators out there, but in order to be with IPv6, would you advise that they do it by hand when you're beginning the subnetting, or just use the calculators to start with?
So I guess it depends, you know, is the classic answer, but it really depends upon how complex your network is and what you want to do with it. If you stick, again, to the nibble boundaries, the individual hex digits, you know, creating IPv6 subnets doesn't have to be hard. You know, you can figure out that if you have any given, you know, subnet that you want to make, it's, you know, if you're sticking to the nibble boundaries, then you're simply incrementing the hex digit. And so every address that'll be underneath that is going to be from, you know, all zeros to all Fs, you know, underneath that particular that particular digit, to the right of that digit, I guess I would say. So, you know, subnetting, if you, again, stick to the nibble boundaries, can be very simple and figuring out what those are. It's only when you start to get into, you know, deciding that you don't want to, you know, you don't want to just do the nibbles. You know, you want to do something more. Maybe you have, you know, 17 networks, and you just are you're offended by the fact that you have to go and you know, burn up so much address space if you think about it in terms of what you'd have to do if you were to use 2 nibbles. You know, because then you're jumping to 256 locations or whatever, 256 choices. So maybe you want to go and do something there. You know, right now, certainly we're in a space where we have the luxury of not even thinking about the address conservation, not having to think about it as efficiently as we did in IPv4. And so, you know, we can say, well, let me just allocate 2 nibbles to that entire you know, block versus when I have 17, because maybe they'll grow, maybe it'll be, you know, do something on that line. But so I guess my key message is to keep your own life, if you're just starting out, keep it simple, stick with it on using the nibbles on hex digits, and your life will be a lot simpler and more sane as far as trying to do that. So you don't really need those subnet calculators that are online unless you start to get wanting to do something more specific or other pieces like that. If you think about why so many of those subnet calculators have emerged online, it's because in the world of IPv4, we've always been trying to, you know, maximize the usage of individual subnets so that we can be sure that we're getting the right number of hosts, or, you know, so we've always done a ton of subnet planning to do this. I talked to somebody a while back, you know, who was working in an organization for a large enterprise, and he said he spent probably a good 3/4 of his time doing subnet planning. And as he was working with a group that was part of the acquisitions team, and they were bringing in new companies and new entities, and so as they were bringing in new organizations, a lot of his time was figuring out how to integrate these new networks into their new things and maximizing the availability. But that's because IPv4 is based on scarcity. And so you're trying to subnet to make sure you can accommodate that. With IPv6, we don't have to worry about the scarcity of addresses. We've got, you know, 18 quintillion host addresses, so we can think more strategically about how we want to do it. So that's a long answer, but the key is, I think, again, try to stay focused for your own sanity on the nibbles, and then you can do that fairly straightforward.
Thanks, Dan. That makes sense. So, is there any other question? Any question from the floor rather? Okay, so I'll ask another question. I have a question for for Hisham. So the dual stack, when it looks like the most practical thing for people to start with for IPv6. Have you had like of networks where people are doing the dual stack necessarily with public or globally routable IPv6 space, and they're just doing like something to get going in the lab to try out it before they get their own public IP space, or is it a scenario where move on directly to the publicly routable IPv6 space? Like what do you see when you're in AFRINIC?
If I get your question correctly, you're talking about for people doing dual stacking, do they get addresses from AFRINIC, or they, in their test beds, do they use globally routed addresses or not? Is that your question? So yeah, some of the stuff that so out of the things that we saw in dual stacking, and like I said, one of the major issues with dual stacking was usually the vendor feature parity. That the stuff that you were familiar doing on IPv4, the policies that you could set on IPv4, the stuff that you have applied within the policies on your network, not all of them were supported by the vendors. This was an issue. If you started out with IPv6, I don't know. I started playing with IPv6 back in 2004, and that, of course, was a huge thing. The feature parity, of course. A lot of the stuff that you could do with IPv4, you could not do at all over IPv6. However, in the past couple of years, there's been a huge push from the community, from the different ISPs, from the different users, the content, to actually get that up to speed. And I must say, a lot of the work has been done there. You find vendors, and this is part of the IPv6 World Launch initiative that Dan put the URLs to, that actually looked into not only the high-end boxes, but they also looked into the user low-cost budget stuff. So you have at least two that I know of, D-Link and Cisco as Linksys, that had their boxes that supported IPv6 without you even notice, without you even turning it off. The box comes with IPv6 enabled on it. I'm pretty sure other vendors join in afterwards, but these are the ones that I remember from the events. So you even have those CPE boxes at home that actually do so. In terms of operating systems, I think there isn't an operating system out there that doesn't support IPv6 now. Even as I'm not a Windows user, but I know that even Windows XP that did support IPv6, but you needed to go and manually turn it on. I remember Windows saying that they will, and probably Dan can speak more intelligently about this than I can. As part of the world launch, they said that they will put XP to bed by 2014 or something because of that, and every single operating system that came out of that afterwards have IPv6 without the user even knows, so you don't need to go in and turn it on manually. So as far as appliances and hosts and operating systems, stuff is ready for IPv4 and IPv6. If you purchased a device within the past, let's say, 2-3 years, it probably supports IPv6 in one way or another. That support is growing over time. The generic excuse that IPv6 is too expensive has become a generic excuse, because like I said, if you were doing this almost 10 years ago, yeah, I would say you needed big shiny boxes that would support IPv6, and they wouldn't give everything that you needed. Now that is not the case. So yeah, probably, like I said, Dan can talk more about the stuff that came out of world launch.
The net of it is that, I mean, out of World IPv6 launch, World IPv6 launch was really focused around content providers, encouraging them to make their content available over the web, and also to consumer electronics devices, as Tom mentioned, a number of those from Cisco, and actually there's a good range. If you go to the World IPv6 launch website, which I put in there, which is the www.worldipv6launch.org, and there is a list on there of the participants that were there, and you can see, for instance, I'll put a link in the chat for the home router vendors, and those are some of the organizations that committed that they were going to enable that, and the launch, the test has actually been changed, or I should say, the list has grown because the University of New Hampshire Interoperability Lab has been doing some more testing, and actually here's the most recent list of this IPv6 CPE, customer premise devices, and you can, or customer premise equipment, and you can see there a listing of some of the more recent equipment that's there. Like Hisham said, most of the operating systems these days, whether it's Windows, Mac, or Linux, and Unix, any of those, they all have IPv6. In many cases, it's enabled by default. A lot of mobile phones have it. Most of the Android devices and Apple devices have it. And in fact, one of the things we're seeing is that we're getting a lot of traffic uptake on mobile networks, particularly around as LTE has been rolled out in various parts of the world. That network heavily uses IPv6, and so we're seeing a large percentage. Verizon Wireless here in the United States, where I am, is showing about 35% of their traffic is coming over IPv6. So there's a lot of movement on that. We just posted yesterday, over the weekend, Google wound up showing about 2% of their traffic, 2% of the traffic going into Google's properties is now coming in over IPv6. And while 2% doesn't sound like very much, the reality is that's doubled in a little bit less than a year, about 11 months or so. So we're seeing a very huge swing in what it looks like, and that's a tremendous thing of what we're seeing out there. So the combination is there in a number of ways.
Dan and Hisham. So one last call for questions from the floor. We are almost out of time.
I'll just mention, Kevin, while we're looking at that, in addition to the resources we've talked about today, if you'd like a little bit more too, I'll mention that the folks at RIPE NCC, which is as Hisham noted, it's the regional internet registry for Europe and parts of Asia. They came out with some IPv6 transition videos, which are quite interesting in that they're animated videos that kind of walk you through the different technologies that Hisham talked about, and those may be helpful for people. And also, if people are interested in looking at how do they make their content available over IPv6, we put up a white paper, a document earlier this year about making content available over IPv6, which talks again about some of the ways you can help your, get your content, your web content available out over IPv6, which can be a first step that some people make in getting more involved with IPv6. Beyond that, I'd say, I think any of our organizations here, AFRINIC, Orange, or the Internet Society, are all here to help people. So if you have questions, please do raise them with us. We're here to help.
Thanks, Dan. So I don't see questions from the floor. Then in that case, I think we can bring this webinar to a close. I'd like to the presenters, Hisham of AFRINIC and Dan Yoko of the Internet Society for their very informative presentations. This brings to a close the second training webinar on IPv6. There will be others in the year, before the end of the year rather, on various topics which we will communicate to all of you on the various mailing lists. The presentations, the slides, and the video will also be made available soon. We will email those to the various mailing lists as well. So thank you very much for attending this webinar. We hope you found yesterday's and today's webinar informative, and and both of them have helped you come to a conclusion, make a decision to move to IPv6. So thank you very much, and see you all at the next webinar.